Thank you. Good morning. So today we shall cover the topic power and speed of MOS inverters. Let us start with CMOS because, as you know, as I've told you, the CMOS is the most important technology today. So for CMOS, let us see how we can have a rough estimate of power dissipation in CMOS. Power dissipation of CMOS. So you see that when you consider a CMOS inverter, I have already told you a number of times that the load it sees is a purely capacitive load because the input is a MOS capacitance. So MOS capacitance is practically a lossless capacitor. The lossless capacitor, ideal, almost an ideal capacitor. Okay, so the load is a pure capacitance. When this input swings from 0 to high, then you remember this driver transistor changes its state from off to on and vice versa. For example, when the driver is off, that means when Vi is 0, when Vi is 0 or less than equal to VIL, all right, then driver, that means this nMOS, this is nMOS and this is PMOS. nMOS is off, and in that case what is going to happen? This capacitor will be charged to VDD through this path. So during charging of CL, you know that the energy which is dissipated, because there is an RC circuit like this, because the CL is getting charged through this path from VDD. This is off. So this is basically an RC circuit. The only difference between an ordinary RC circuit and this RC circuit is that this R is continuously varying with time or voltage or current, whatever it is, a non-linear resistance. Whereas this capacitor is an ordinary linear capacitance. So be it almost a short circuit or any R, it does not matter. It is, we have to see ultimately this capacitor is charged to what voltage. Depending on that, we know there will be the power dissipation. We say that this power is stored, means actually this power is dissipated in this resistor. And you know, during this cycle, when, or rather during the half cycle of the input clock, when this output capacitor is charged to VDD, the power dissipation is simply equal to half CL into VDD square. This is the power dissipation during charging. Please remember that in the steady state, no power dissipation. There is no power dissipation either Vi when Vi is equal to 0 under steady state, or Vi is equal to VDD or VDD, or you can call it VIH, or more than VIH. In this two steady state under DC condition, the current in the chain is practically zero, and therefore power dissipation is zero. So steady state power dissipation in CMOS is considered to be zero or practically negligible. Whatever power dissipation that takes place in CMOS inverters is during the transitions. So when there is a transition, from high to low, high to input, high to low, that means this transistor is driven off from on state. Then during that time, what is happening? This capacitor is gradually getting charged to the full voltage VDD, and the corresponding energy stored, as well as the charge, which is energy which is dissipated in the corresponding RC circuit, our resistance here in series resistance, is nothing but half CL with this fundamental, that capacitor charging circuit is like this. Similarly, in the next cycle, when BI makes a transition from low to high, off to on, the nMOS changes its state from off state to on state. Then correspondingly, in a complementary fashion, the PMOS changes its state from on to off. The PMOS becomes off in the steady state ultimately, and this kappa charge, whatever is earlier stored in the capacitor, will be discharged through this nMOS, and this voltage will tend towards zero. So if you have a capacitance charged to a voltage V and then discharged fully through any resistance, so what is the energy dissipated, or what is the energy lost by this process? Again half CV square. Again half CV square. Therefore, during the discharge process, again another power is half CL VDD square. Again is the power dissipation during discharge of CL. Okay? And therefore, the power dissipation per cycle, per clock cycle is equal to simply CL VDD square. Or in fact, this should not be called power dissipation, energy dissipation. I should correct it. This is energy. This is energy, not power, definitely. Energy, and this is also energy. Energy dissipation during charging of CL and energy dissipation during discharge of CL. And therefore, again, it is not power, it is energy. This is a mistake. Per clock cycle is this. Therefore, the power dissipation. Power means energy in 1 second, per second. Power dissipation is simply equal to CL VDD square into frequency of the clock. F is equal to clock frequency. So this is a very important, very simple derivation, but it is very, thought-provoking in the sense that it gives a lot of, knowledge, lot of indications about how to optimize this power dissipation. You just see that power dissipation in the CMOS, which takes place only during the transitions and not in the steady state, is proportional to the clock frequency. Very important observation. Is proportional to clock frequency. is proportional to the load capacitance. Naturally, higher is the load capacitance. If there is a lot of fan out, power dissipation will be more because you have to charge a larger capacitance. And the very, very important observation is it is proportional to VDD square. It is expected, of course. But anyway, in mathematical form, we'll find the power dissipation is proportional to the square of VDD. Now, ultimately, you see that when you have to use a CMOS at a very high clock rate for the most advanced VLSI. Okay, as you know, nowadays people are designing VLSI, fabricating VLSI, which is working at hundreds of megahertz, even gigabits per second. People are pursuing that clock rate. Okay, in that case, perhaps we have to reduce the power supply in order that, because F is increasing too much. F will be a very, very important factor. Then to minimize power, the supply voltage reduction is a very, very important thing to be considered. That is why that why the present generation VLSI is gradually tending towards lower and lower supply voltage. Of course, it is now limited to around 1 volt, 3 volt and then 1 volt. And that is due to this power dissipation in CMOS. That is a very primarily important thing. And it also has some other advantages. For example, the various high voltage induced effects in CMOS that is got rid of. But the problem is of noise margins. It will be more susceptible to noise. But unfortunately, you can design systems, or fortunately, you can design systems in such a way that noise is minimized. So that's how the present generation CMOS has got a tendency to have a power supply voltage which is lower and lower, but below 1 volt there is practical difficulty imposed by noise margins. So up to 1 volt or 1.1 volt is a limitation imposed by the various considerations today. And clock frequency, of course, nowadays the highest clock frequency which has been achieved is no limit, but commercial stage, as you know, several hundred megahertz. On non-commercial research stage, gigabits. Okay? And what about the CL? CL is nothing but the input capacitance provided by a similar inverter. And if the fan out is 1, in that case, CL can be written as, what is the value of CL? Simply COX multiplied by WP LP plus WN LN, where COX is the oxide capacitance per unit area. Oxide capacitance per unit area. And already you know what are WPLP and WNLN. So you can easily calculate the value of the capacitance if the fan out is 1, and very easily estimate the value of the power dissipation. So why don't you take a problem on this? Just do it. You find, just note down, find a problem. What is W? W means the power dissipation. I am calling it W. What is W if, say, WP is equal to, let us assume that WP is, this is CMOS, is it not? WP is 10 micron and WN is, let us assume for simplicity again the same 10 micron, though it may not be exactly 10 micron. LP, LN are equal to 1 micron, and oxide thickness is 200 angstrom, and power supply voltage VDD is 3 volt. Do you need clock frequency? Yes. and clock frequency f is equal to 50 megahertz. And you just try to estimate this figure, how much it comes, and report it to me earlier. You will find it will come to a very, very small order compared to the participation in conventional logics, other than CMOS and other forms of logic like TTL and nMOS or ECL gates. Okay? So our conclusion about the power in CMOS is that whatever power dissipation that takes place in CMOS is during the transitions from 1 to 0 and 0 to 1, and this power dissipation is proportional to the clock frequency, proportional to the square of the supply voltage, proportional to the load capacitance. That means it is also proportional to the fan out. How many such inputs have been connected to the output, and that is a very important factor to determine the power dissipation of a particular logic. Next, let us come to the single channel inverter cases. Single channel inverters cases. In the case of saturated load, you know that the load transistor, for single channel inverters, the load transistors are always on. It's not like CMOS. CMOS, load transistor gets on and off along with driver transistor in a complementary fashion. However, for single channel inverter, MOS inverter or PMOS inverters, the load transistor is always on. Whatever it may be its state, it may be a depletion mode device, it may be an enhancement mode, in saturation or in linear or triode region, but this is always on. In that case, when V0 is 0, that means when Vi is high, when input is high, the output is in the low state. The driver transistor is heavily in on condition. The output voltage is near 0. All right? And in that case, whatever will be the chain current, that will be the maximum current, and the corresponding power dissipation will be the maximum power dissipation in the MOS. So what we do normally, we simply calculate the power dissipation in the inverter chain when VO is 0. That means when Vi is high. All calculations are performed like this. When Vi is more than equal to VIH, and we assume that VO is practically equal to 0. Under this condition, you remember for saturated load, the drain current is given by beta L by 2 into VDD minus VT whole square. We have already seen it because the load in saturation, and therefore the power dissipation P is simply given by VDD into IDL, because VO is 0. VO is 0. So VDD is the effective drain by VDS of the load transistor. Because VO is 0, the VDS of the load transistor is VDD multiplied by IDL, and that is simply equal to beta L by 2 into VDD minus VT whole square. Our observation is that in this particular case of saturated load, the power dissipation depends. It is a standby power dissipation, and which is much more than the transition power dissipation. So transition power dissipation can be ignored in this case. It is a standby power dissipation when Vi is high, or in this case Vi is high or low. It depends on, you can calculate, but this is the maximum power of the two. It is the normally when we speak of power dissipation in saturated load or a single channel inverter, it is this power dissipation which you consider, and you see that it is very sensitively dependent on VDD. In fact, it is proportional to roughly VDD cube. There is practically no dependence on clock frequency because power dissipation during transitions is negligible. It is this power dissipation which predominates, and it is proportional practically it is proportional to VDD cube. It is proportional to beta L. That means if the W by L ratio of the load transistor is large, the power dissipation is more. And what we want to maintain usually? The driver transistor W by L is usually large compared to the load transistor. That way we automatically that is taken care of because beta L is tried to keep smaller than beta D in order to achieve the desired performance of DC performance of the single channel inverter. Beta L is kept less than beta D. So that is automatically taken into account. However, VDD dependence is quite sensitive. It is practically proportional to the cube of VDD. Take the case of triode load or linear load. Linear or triode load. In this case, ideal is equal to beta L by 2 VDD into twice VGG minus VT. Yeah, VDD is taken out, VDD. And under the same condition, when VO is equal to 0, the power dissipation is given by, therefore this multiplied by VDD and given by beta L by 2 VDD squared into twice VGG minus VT minus VDD. Here you see that power dissipation, if you compare these two expressions, here the power dissipation, you just note that there is another term dependent on VGG, but that is not that important. Again, for this inverter also, it is a VDD cube which comes into picture. VDD cube, because VGG and VDD, if it is of the same order, VGG may be a little bit more than, actually in this case VGG is more than VDD. So you see the dependence on power supply voltage is too much. So if you can gain a lot in the case of single channel inverters if you can reduce the power supply. That is what I wanted to say. If you want to reduce the power dissipation of these single channel inverters and the logics derived from these single channel inverters, then reducing the power supply voltage really will be tremendously beneficial. It will be more beneficial than CMOS, which is observed through these expressions. Then the case of depletion mode load. And in this case, ideal is equal to beta L by 2 in Vp squared when the load is in saturation under V naught is equal to 0 condition. And therefore the power dissipation is simply beta L by 2 VDD into Vp squared. By Vp here I mean V capital P, I am writing V, it is a pinch of voltage. You remember Vp is pinch of voltage. Alright? And this is again another indicator of the depletion load that here the dependence on VDD is much less, proportional to VDD, but it is dependent on the square of the pinch of voltage or threshold voltage. Same thing. Pinch of voltage and threshold voltage is the same of the load transistor. Please remember, I am referring to load transistor. This is the pinch of voltage of load transistor. Don't get confused. Remember, the load transistor is a depletion mode transistor and its threshold voltage is usually called pinch of voltage. And it is proportional to the square of that pinch of voltage. So if you reduce the pinch of voltage, so for as power dissipation will be a lot of benefit. But what is the drawback of reducing pinch of voltage? if you remember. If you reduce it too much for just reducing the power dissipation, what is your problem? Noise margin. So, as you have seen that, we have to make a trade-off or compromise between the various parameters to achieve optimum performance in all respects. We have to we have to consider not only the power dissipation, we have to consider the DC levels, logic swings, noise margins, and over and above that, the speed. Okay? Considering all these things, so these are some formulae which indicate how the different parameters, how the different output things, specification outputs are dependent on the various device parameters, circuit parameters, and voltage levels, etc. So this is in short the power. Now how you can get simply the expressions for power dissipation in MOS inverters, and how you can have some kind of optimization of these power dissipations in the various inverters. Our conclusion at the end is that the CMOS is definitely the best, so far as much better, very, very good compared to any other form of inverters, so far as power dissipation is concerned. But what is the drawback of CMOS? The only CMOS inverters, in the case of CMOS inverters, the power dissipation is dependent on the clock frequency. Here also they are dependent, but that is very, very small. In this case also clock dependence, the transition dependence is there, but the standby power dissipation is usually much more important than those powers. But in CMOS, if it is not working, no power. That's an advantage. And it is found in practice that for a lot of time, unless if you go for the today's tendency of parallel processing and all these things, when you try to make the chip busy for the entire cycle, all parts of the chip uniformly busy always, then only there are a lot of power dissipation in CMOS comes in. Otherwise, the previous designs, when particularly in computers, when parallel processing concept did not come, okay, in that case, for most of the time, it is found that many of these devices are not working, and that happens. And as a result, the total power, say in our watch chip, for example, it is the best example of watch chip. It is quite a complicated chip, and its power distribution is so clock chip, everything. It is such that a small battery can be used for years without any problem. We now consider the speed. In fact, when we consider the transient response of the MOS inverters, actual analysis is very, 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 very difficult. And in fact, beyond the scope of this class, because a lot of device physics will come in. Okay? So we are not going to take that path. It will be maybe the full semester course can be devoted on simply analyzing the MOS inverters in their transients, because a lot of device physics is involved. Rather than that, we shall adopt a path which is simpler and which can be at least applied readily in this class simply from our circuit knowledge. Let us draw again the basic inverter circuit. Okay, let us draw the basic inverter circuit once again. Okay? Now we shall assume that the intrinsic device speed is much higher than the circuit limited speed. That is, I write that intrinsic device speed is very, very large compared to the circuit limited What I mean by that is very, very large, intrinsic device speed is very, very large compared to circuit. What do you mean by this? I mean that if I want to turn this device on and off, the driver transistor, by applying a sharp signal, it will immediately respond. If I want this transistor to be off at this moment, it will be turned off at this moment. I say precisely at this moment. If I make a transition at Vi from high to low, this should be turned off immediately without any delay. Similarly, if I turn it, if Vi makes a transition from low to high, it will turn off immediately. Turn on immediately. Then what is meant, that you can now ask me that if I assume that basic thing in the beginning, then what is the necessity of going through that transient analysis? I am assuming the device is very high speed. No, actually what happens, you see that this device, which is a load transistor, is a substitute of a practical ordinary R, ordinary linear resistor. That is why it is called an active load, a non-linear resistance. When this is turned off, this capacitor gets charged through this path, and that takes time because after all there is an R, and this R is provided, RC time constant involved, and this R is provided by this. Only thing is this R is dependent on time. R is dependent on time, or another, in this case, voltage and current, and therefore time. So even if this transistor is turned on and off immediately, it does not matter. Charging will take some time because of this path. Am I correct? Similarly, when I make this transistor suddenly a low to high transition, that means initially it was off, then it is turned on. It will be turned on, but it will offer a resistance. I have not said that it is turned on to zero resistance. That I have not said. I have said that it will turn on to a certain, that variation of resistance, just as happened in the case of the load transistor. Therefore, the discharging will also not be an immediate process. If this resistance, if I had said that yes, it is turned on to absolute zero resistance, then naturally discharging would have been an instantaneous process. But that is not what I am saying. I am saying that this transistor will respond to the input signal without any delay. But otherwise, its variation with resistance, the I versus V relationship remains as it is. Therefore, you see that even if I assume that these two transistors work instantaneously with input signal, their intrinsic device speed is very high, then also there will be some delays involved arising from the processes of charging and discharging. Now, in order to, that I cannot make such a certain assumption like this. Let us try to justify it. For justification purpose, we shall bring a parameter called F max, which is equivalent to Ft of bipolar unity gain frequency, and this is found to be equal to Gm of the transistor divided by twice pi Cg. Cg is the gate capacitance. Same as Cl, whatever I have written there. F max is the cutoff frequency of maximum usable frequency. Not exactly, F max is nothing but the cutoff frequency Ft, where the output current is equal to, at this frequency the output current is equal to the input current. You can easily derive it. simply by drawing the equivalent circuit of MOSFET and see that at what frequency this is happening. At what frequency the output current is nothing but Gm into VGS. You remember the equivalent circuit of a MOS inverter or MOS inverting amplifier, for example. Then the output current is nothing but Gm into VGS, and input current is equal to VGS divided by the reactance 1 upon omega Cg, and these two are equal. Equate them, you will get this. It is this frequency at which the output current equals the input current, maximum operating frequency of a MOS transistor. Now, in this case, as I told you that Cg is the gate capacitance given by COX into WL, and Gm is the transconductance given by beta into VGS minus VT, and ultimately, and COX is also given by, you know, the formula is simply epsilon OX divided by TOX. Epsilon OX is the permittivity of the dielectric, the gate oxide. This is the permittivity of the gate oxide, is the thickness of the gate oxide. TOX is the thickness of the gate oxide. COX is the oxide capacitance per unit area, the standard thing. And substituting all of them, we get, here, we get F max is equal to, as well as the expression for beta, which I've already given you earlier, you get an expression which is something like mu n divided by twice pi L square into VGS minus VT. Mu n is the electron mobility in the case of n-channel inverters, n-channel MOSFETs. L is the channel length. If you substitute all of them, ultimately you get a result something like this. You remember in the Gm expression also there is a COX, so COX cancel out, and ultimately you get an expression like this. And here you see that F max is proportional to the square of, inversely proportional to the square of L. So if I can reduce L, the channel length, there is a lot of benefit. Proportional to mu n, for electron nMOS it will be higher definitely as indicated, and proportional to VGS minus VT, it is more or less standard thing for all kind of this. It is not a that important parameter. The most important mu n and divided by L square. And if you make some typical calculations for any ordinary MOSFET, you will find that F max is coming out to be of the order of a gigahertz, or maybe much more than around 1 gigahertz, or at less than, or even it may be much, today's MOSFET it may be much more than that. So we can say that from this thing we can conclude that the device will function from on, that means the switching of the device from on to off can be considered to be practically an instantaneous process compared to the charging and discharging times, which are nothing but circuit limited speed. Charging and discharging is nothing but circuit limitation. That speed is limited by the RC. That is what I call circuit limited speed, whereas the intrinsic device speed is determined by this F max. And because usually F max is very, very large, therefore we can assume that yes, this driver transistor will be turned on and off immediately. Alright? Now let us consider first a case which is called high to low transition. Input Vi is high to low. So Vi I am plotting, it is a signal like this. So Vi versus time, this is t is equal to 0. So this is high and this is low. So you see that for t less than 0, Vi is equal to V, which is a high state, which is greater than equal to VIH, whereas for t greater than equal to 0, Vi is 0. greater than or greater than, you know that in the limit, so I should not, let me drop that. Greater than 0, Vi is 0. So it is called a high to low transition case. In this case, for saturated load, so we are considering inverters, single channel inverters with both transistors enhancement mode. We are considering, so saturated load means the case which is called NELS for N channel device. The ideal, the load current, you remember, is given by beta L by 2 into VDD minus V naught minus VT whole squared, and that can be expressed in this fashion: beta L by 2 taking VDD minus VT outside into 1 minus V naught divided by VDD minus Vt, and that is whole squared. And this can be ultimately written in the following form, which is beta L by 2 into VOH squared into 1 minus U squared, where U is the normalized output voltage, which is VO divided by VOH. All right, so I can write ideal in this particular form now. It's very simple. I call it 1, equation number 1. Similarly, for the case of the triode load, for linear or triode load, we have already expressed ideal in the following fashion. Please refer to our earlier lectures. Equation number 2, we have already expressed, where you remember M is a biasing parameter. I am not rewriting that. Please refer to that earlier equation. U is the same normalized output voltage. And if I look at both these equations, equation number 1 and equation number 2 simultaneously, if you look at both these equations simultaneously, then I can write down a general expression for ideal valid for both linear and saturated load, and which is like this: ISC into 1 minus U into 1 minus MU, where ISC is defined as, it is a short circuit current, is simply ideal when V naught is equal to 0 and AM is equal to 1 represents saturation, which I have already discussed earlier. You look carefully. This is the expression for, this is an equation 1 valid for saturated load, equation 2 valid for linear or triode load. I can represent both of them by this single equation I3, where this part, this BL by 2 into VOH square, or BL by 2 into VDD is again VOH square by M, is simply ISC. You just see that when M is equal to 1, this is the same thing, because VDD is VOH. In load saturation case, VOH is VDD minus VT. In load, in triode case, it is simply equal to VDD. So this is again VOH. Effectively, VDD square means VOH square. M is equal to 1 means saturated load, and this beta L by 2. And when U is equal to 0, that means VO is equal to 0, this part is unity, So it is nothing but ISC is therefore nothing but equal to ideal when VO is equal to 0. It is a load current when output is short circuited. That is why I have given the name ISC. So I have represented both the equations by a general equation for the sake of mathematical convenience, in order that I can analyze both the inverters simultaneously instead of making separate analysis. Then you see that for t greater than 0, we have seen that the driver transistor is off. Am I correct? For d greater than, input is low, so driver transistor is off. Therefore, in that case, ideal IDD must be equal to 0. Driver off. Input is low, driver is off. High to low. So for greater than t greater than 0, driver is off. So in that case, the IDD is equal to 0, and therefore we can say that IDL is simply equal to IC. In fact, not I, call it IL, the load current. And if you refer back to again the earlier diagram, the load current, this is IL. So it is nothing but the current through the load capacitance. Okay? So when IDD is equal to 0, IDL is simply equal to IL, which we ignored earlier. You remember in the earlier analysis, we assumed IL is equal to 0 because simply that was the DC analysis. In the steady state, no scope, IL is 0. But now we are making a transient analysis, so IL is non-zero. Okay? So that's the difference. Therefore, under this condition, we can rewrite from this equation, ultimately, this ideal is equal to IL gives you CL. What is IL? IL is simply equal to CL into d V0 dt. Voltage across the capacitor is V0. So CL V0, and that is equal to ISC into 1 minus U into 1 minus mu, and which can be rewritten like this: CL into du dt is equal to ISC divided by VOH into 1 minus U into 1 minus mu. All right? Then what is the significance of VOH divided by ISC? Can you tell me what is the significance of this? I call equation number 4. What is the significance of VOH divided by ISC? VOH is VDD minus VT for saturated load or VDD for triode load. And ISC is a short circuit current when VO is equal to 0. So what is the significance of this? When VO is 0 means at t is equal to 0. When we have assumed that already steady state has been achieved and the output capacitor has been fully discharged through the load, so VO is practically equal to 0. So at t is equal to 0, I am assuming VO is 0. So what is the voltage across the load transistor in that case? At t is equal to 0, what is the voltage across the load transistor VOH? And that divided by the current is the initial resistance. So it is a resistance offered by the load at t is equal to 0, and thus we can define a time constant tau, which is the product of this and CL, that is equal to CL into VOH divided by ISC, is the initial or rather time constant I can say in the initial, at the initiation of the process or at t is equal to 0. And ultimately replacing, should I stop now? So let me stop for a few minutes and then I shall break for a few minutes and then I'll start once again.